Welcome to video 20 in our series on tensor calculus. In this video, we're going to explore a number of algebraic operations involving tensors. This is the format we used in the previous video to define the components of a tensor. Well, if we continue to use this format as we talk about the operations of tensors, the results are going to become way too complicated and unwieldy. So what I'm going to do is just give you specific examples, and from there you'll easily be able to generalize the results. We'll begin by talking about what it means to say that two tensors are equal. Here we have two tensors, A and B. They each have 6 indexes, which means they're both 6th ranked tensors. Well, in 3 dimensions, there would be 3 to the 6th power, or 729 individual components for each of these two tensors. Well, to say that they're equal is to say that each of the individual 729 components of A is equal to its corresponding component in B. We match them up on a one-to-one basis, and if they're all equal, then we said that the two tensors are equal. Now, of course, for anything like this to make sense, these two tensors have to have the same index structure, and they do. They both have ijk on the top, and they both have rst on the bottom. But let me quickly point out that it's not necessary for these indexes to be in the same order. For example, we could extend this comparison to a tensor C that has these indexes. C has ij and k on the top, it has rs and t on the bottom, but in a different order. Now that's okay because we can still establish a one-to-one correspondence between tensors A and B with tensor C. So, equality is a pretty simple concept. Two tensors are equal if and only if each of the individual components of one is equal to the individual components of the other on a one-to-one basis. All right, let's move on now to addition. Here we're adding tensor A to tensor B to get tensor C. Now in each case there are 4 indexes, which means we're talking about 4th ranked tensors. In 3 dimensions, there would be 3 to the 4th power, or 81 different components for each one of these terms. So what we're saying with an expression like this is that we are performing 81 different addition operations simultaneously. We're adding each component of A to its corresponding component of B to get the corresponding component of C. It's really a very simple and straightforward concept. Well, just like for equality, for this to make sense, the index structures have to be the same. We have to have the same indexes on the top, and we do, ij all the way across the board, and the same indexes on the bottom, r and s in this case. And as before, it's not necessary for these indexes to be in the same order. We have to have the same indexes on the top and the same on the bottom, but they can be in any order. Well, now let me pose this question. Suppose we know that A is a tensor and B is a tensor. What does that say about C here? We know that we're going to perform 81 addition operations. We'll get 81 different answers, and we know that we can express those 81 answers in an index structure like this, but does C actually represent a tensor? Well, the answer to that is yes, and let me show you how we prove it. First of all, we express the relationship using the prime coordinate system, like this. Now we multiply through by a set of Jacobian factors that are very carefully chosen. We've chosen this set of Jacobian factors such that I and j prime match up here, r and s prime match up here, and I and j match up here, and r and s match up here. Well, you know from the previous video that that means that this is a transformation from the primed coordinate system back to the unprimed coordinate system. We multiply by these Jacobian factors, it will transform back to the unprimed system. Well, we've multiplied the entire expression here by the same Jacobian factors, and when we do so, this product right here is what we need to transform from B prime back to B. So this expression right here is exactly the same as this one. So now that we know that this equals this and this equals this, we can substitute these values in place of those and get this relationship. Okay, well now that we know that this equals this, we know that this equals this. And that gives us our proof. We see that C transforms from the primed coordinate system to the unprimed coordinate system using these Jacobian factors. And remember from the last video that these indexes matches dummy indexes, these matches dummy indexes, and these two remaining ones here match this, these two remaining ones match this, and so this is the transformation of a tensor, and that proves that C is in fact a tensor. Now I'm sure you can see how this generalizes. For example, if we had another index, if these were fifth ranked expressions, then all that would happen is that we would be using 5 Jacobian factors across the board, and as we work our way down, we'd see that this would be a fifth ranked tensor, and everything would work out just right. You can also see that we don't have to limit this to just 2 terms. We could add 3 tensors together, or we could also insert subtraction. It's easy to see from this proof that whenever we combine any number of tensors of the same rank and index structure together with addition and subtraction, the result is always going to be a tensor. Now, the thought may have occurred to you whether the converse might be true. In other words, if we know that C is a tensor, what does that mean about terms A and B? Would that mean that these would be tensors as well? And the answer this time is no. It's entirely possible to form a tensor like this by adding 2 terms together that are not tensors themselves, but when they're added together they produce a tensor. Not only is this something that's possible, but we're going to see important examples of this in future videos. Okay, let's move on then to scalar multiplication. Scalar multiplication is really easy. When we say we're going to multiply tensor p by 5, we simply mean we're going to multiply each component of tensor p by 5 to get the corresponding component of q. Well, let's pose this question. If we know that p is a tensor, does that mean that q is a tensor? And the answer is yes. And the proof is very similar to the one we used for addition. We start by expressing the relationship in terms of prime coordinates. Then we multiply by the Jacobian factors that will transform p back to the unprimed system. So adding these Jacobian factors combined with this is the same as the tensor in unprimed coordinates, which means that this statement is now true. And because this is equal to this, then this is equal to this, and that completes the proof. This is the set of Jacobian factors needed to transform Q from the prime system to the unprimed system. Multiplying a tensor by a scalar value will always produce a tensor. Well, now take a look at this expression. Suppose we know that A is a tensor, B is a tensor, and C is a tensor. Well, based on what we just saw with scalar multiplication, we know that this would be a tensor, and this term is a tensor, and this term is a tensor. And based on what we learned about addition and subtraction, we know that combining these terms with addition and subtraction will then produce a tensor over here. So we can sum all this up by saying that operations with tensors are linear. Okay. Let's move on now and take a look at a different kind of multiplication. This time we're going to multiply 2 tensors together. We've got a second-ranked tensor and a third-ranked tensor. So what we're going to do is multiply each of the components of p by each of the components of q. Well, p is a second-ranked tensor, which means in 3 dimensions it'll have 3 squared or 9 individual components. Q is a third-ranked tensor, and it will have 3 to the third or 27 individual components. As we multiply them together, we're going to get 243 answers, individual components on the right-hand side. And to capture that, we need all 5 of these indexes. Notice that the number of indexes here is equal to the sum of the indexes on this side. In other words, the upper indexes here match the upper indexes there. Likewise, the lower indexes match here. Well, we call this kind of operation an outer product, or a tensor product. Let me say a word here about the index structure. One of the syntax rules of tensor calculus is that we cannot have any duplicate indexes in either the upper or the lower position. And what that means for an outer product is that when we begin to choose the indexes for a factor like p here, we have to make sure that the upper index is not equal to r or s, and the lower index is not equal to k. The indexes we choose here must be unique on both the top and the bottom. Now, it is permissible from a syntax perspective to choose an index that might duplicate a bottom index with the one on the top. This would be forming a dummy index, and syntactically it is okay and correct, but that would not be an outer product. That's a different result that we're going to discuss in the next video. For now, just be aware of the fact that for an outer product, the indexes that are chosen need to be unique across the board. Notice the upper indexes here match these, and the lower indexes here match these, and there are no duplicates. Well, now let's pose the question, if we know that P is a tensor and Q is a tensor, do we know that R is a tensor? Well, by now you know the drill. We start by expressing the relationship in prime coordinates. Then we multiply by the Jacobian factors we need to transform the known tensors back to the unprimed coordinate system. And that would be these. These two Jacobian factors will transform P prime back to P, like this. These three Jacobian factors will transform Q prime back to Q. And of course we multiply these 5 Jacobian factors on the right-hand side to keep the equation in balance. And that means that we know this relationship, and because we now know that this equals this, then this equals this, and that completes the proof. We see that these Jacobian factors will transform R from the prime coordinate system to the unprimed coordinate system, and that means that R is indeed a tensor. So, in summary, we can produce a higher ranked tensor by forming an outer or a tensor product between two lower ranked tensors. Well, interestingly enough, the reverse operation is possible as well. So let's go see how it's possible to take a higher ranked tensor and decompose it into the products of lower ranked tensors. We'll start with the simplest case. There's a theorem that says any second-ranked tensor can be decomposed into the sum of vector products. Now these, of course, are outer products or tensor products, but since all the factors are vectors, then we can call them vector products as well. The number of terms we need is going to be equal to the dimension and the space that we're working with. So this is what's required for a three-dimensional solution. If we're only working in 2 dimensions, we'd only need 2 terms. If we're working in 4 dimensions, we need 4, and so on. Well, the theorem says that we can choose vectors x, y, and z here arbitrarily. They can be anything we want, as long as no 2 of them are parallel to each other. And having done that, we'll be able to solve for vectors a, b, and c to make this relationship work. Now, rather than trying to prove all that, let's just illustrate how it works. Suppose our second-ranked tensor looks like this. These are just components I've made up. But if we had these components for a second-ranked tensor, then this would be a potential solution. What we could do is to choose vectors x, y, and z. In this case, x is a unit vector pointing in the x direction. That's just x hat. Y is a unit vector pointing in the y direction, and z is a unit vector pointing in the z direction. Well, having selected those, then we'd find that vectors a, b, and c would have these values respectively. Okay, well, let's see how this works. Let's calculate the value of component W11. According to our formula here, that's equal to A1 x1 plus B1 y1 plus C1 z1. Well, A1 is 5, x1 is 1, so this term is 5. B1 is 2, y1 is 0, this term is 0. C1 is negative 3, z1 is 0, this term is 0. Add them together, we get 5, and that's the value of W11. Well, let's do it again. Let's try W, 2. Let's do that. This would be A2 x2 plus B2 y2 plus C2 z2. A2 is 6, x2 is 0, this term is 0. B2 is negative 4, y2 is 1, this term is negative 4. C2 is 1, z2 is 0, this term is 0. Add them together, we get negative 4, and that's the value of W22. All right, well, I'll let you play around with this and convince yourself that it works in every case. Now, this, of course, is not a unique solution, but the point is that we can always decompose a second-rank tensor using this technique and decompose it into the sum of vector products like this. Okay, let's look at a more complicated example. What we'll do now is to extend the analysis to a third-rank tensor. And the same theorem tells us that we can decompose a third-rank tensor into tensor products that look like this. Same number of terms, but this time each factor consists of a vector and a second-rank tensor like this. Okay, well, what we can do next is to decompose each of these second-rank tensors using the technique we used here. So we can break those down to look like this, perhaps. Now we can take these values, substitute them back up in here, and we can expand the whole thing out to look like this. What we have now is a set of 9 vector products added together to represent this third-rank tensor. Okay, well, when all is said and done, we can extend this technique to any rank we need to. It tells us that a tensor of any rank can be decomposed into a set of vector products. And the theorem tells us that the number of terms that we're going to need to do this is going to be n to the r minus 1, n being the dimensions in the system we're working with, r being the rank of the tensor, and each term is going to have r factors. Okay, so looking at this case right here, n is 3, r is 2, so n to the first power is 3 terms of 2 factors each. Here, n is 3, r is 3, so 3 squared is 9 terms, and each term will have a total of 3 factors. Well, all of this is very interesting, but we very seldom, if ever, have to actually decompose higher-ranked tensors in this fashion. The importance of this theorem lies in the fact that we know we can do it if we have to. And what that does is to give us a tool to work with as we go about proving certain properties regarding higher-ranked tensors. And we'll use this theorem later on for just that purpose. Okay, with that, let's take a break and review everything that we've done thus far. We started by defining the equality of tensors. We said that tensors A and B are equal if and only if every one of the individual components of tensor A is equal to its corresponding component in tensor B. Now, for that kind of comparison to make any sense, the two have to have the same index structures. They have the same indexes in the upper position and the lower position. But we pointed out that they don't necessarily have to be in the same order. Could be something like this, but it has to be the same indexes here and here throughout the comparison process. Okay, well then we moved on to addition. And what we discovered there is that the addition is simply a matter of adding each component in tensor A to each corresponding component in tensor B to get the corresponding result in C. We'll add each one of them together as individual additions, and that'll produce a tensor as a result. We noted that if A and B are tensors, then C is always going to be a tensor. We also noted that the converse is not necessarily true. Just because C is a tensor doesn't mean that A and B are tensors. Next, we looked at scalar multiplication. We said that multiplying a tensor by a scalar is just a matter of multiplying each of the individual components by that scalar to give the result. And we derived the fact that if P is a tensor, then so is Q. It's a very simple operation, and if P is a tensor, Q is a tensor in every case. All right, now taking those two results together, we discovered that tensor operations are really linear, that each of these terms will be tensors because of this relationship, and then added together, this is a tensor because of this relationship. The operation with tensors is a linear operation. If A, B, and C are all tensors, then D is going to be a tensor as well. Next, we introduce the concept of an outer product or a tensor product. And what we do here is to take every component of one tensor and multiply it by every component of a second tensor, and that produces a system R here. We noted that it's always the case that when P is a tensor and Q is a tensor, then the result R is going to be a tensor as well. And we pointed out that for this to work, these indexes have to be unique. We don't want any of the indexes in P to be the same indexes as in Q. And when that's the case, we have what's known as an outer or a tensor product. We also pointed out that the rank of the result, the result is always going to be a tensor, and the rank of that tensor is going to be equal to the sum of the ranks of the two inputs. So by multiplying a second-ranked tensor by a third-ranked tensor, we will produce a fifth-ranked tensor like this. Finally, we demonstrated that a tensor of any rank can be decomposed into the sum of vector products. Here we decomposed a second-ranked tensor into the sum of 3 vector products consisting of 2 vectors each. Here we decomposed a third-ranked tensor into the sum of 9 products consisting of 3 vectors each. The general rule is that the number of terms will be equal to n to the r minus 1 power, n being the dimension of the space we're working with, and r being the rank of the tensor. And each of the terms in the decomposition will consist of r factors each, again r being the rank of the tensor. We'll make use of this result in future videos as we demonstrate some of the properties of higher ranking tensors. Okay, with that we're done. In the next video we'll continue our exploration of tensor algebra as we introduce the concept of contraction.